Okay, let's begin. I am very pleased to talk to you and to have a little tour through Field Cycling NMR Relaxometry. The main purpose of the technique is to measure the frequency dependence of the spin lattice relaxation time or of the relaxation rate. And the question is, how can we do this in a field range as wide as possible? And especially, what information can we deduce from such data sets? Okay, in this talk, I will first describe a typical experimental scheme, including the limits of applications, and then we will discuss a statistical theory behind all that, and this especially refers to correlation functions and spectral densities. How can we calculate such functions? As applications, I'm going to discuss liquid crystals, polymers, and porous media. And finally, I will outline the so-called flow relaxation effects. That's this superposition of hydrodynamic flow and ordinary Brownian motions. And at the end, I'll give some take-home rules which might be useful for interested people. Okay, have a look at the diagram where we plot the external magnetic flux density versus time. We first switch the field on to a certain polarization field level as high as possible. And then we switch the field down to a variable relaxation field. And then we switch back up to a high level where we can detect the signal with a 90-degree pulse or with a echo sequence. Now the magnetization will develop as shown here. First, during the polarization field, we will reach a high magnetization. And then in the lower relaxation field, the magnetization will decay, and we can probe this relaxation curve point by point by switching up to the acquisition field and detecting the signal. So this relaxation curve is probed point by point, and the solution of Bloch's equation is given by this expression, where we have here the spin lattice relaxation time as a function of this field level. So quite important, we have assumed a mono-exponential relaxation curve here, as it is usually the case in homogeneous media. In some cases, in heterogeneous samples, there might be a superposition of exponentials, which makes things much more complicated. Now we can also vary the relaxation field, and in this way we can record a data set of this relaxation time or the relaxation rate as a function of the relaxation field. Okay, there are some critical points which have to be taken into account when doing such experiments. The first one I would like to refer to is this edge. It's relatively easy to go from the polarization field down to the relaxation field. This is not a big problem technically. However, when we reach the relaxation field, the field should settle immediately. I mean, we have relaxation times as short as just 1 millisecond, and therefore this field should settle within a millisecond or better less, within a few percent. There should be no oscillations or overshooting. If you have any doubts whether your system is reliable in this respect, you can use a standard sample like PDMS or polyglycine, as shown here, and then you can do a test experiment, and whenever you can reproduce the known dispersion at low fields, you can be sure that your system is okay. When we detect the signal in the acquisition interval, time is not that critical because relaxation times tend to be longer at high fields. However, since we want to reach magnetic resonance, this field should be reached within 10 to minus 5 to 10 to the minus 4. And this may be also quite important. A further point may be the duty cycle. We are working with a resistive system, and if we have high fields, there might be thermal effects we would like to avoid. Finally, there are some conditions concerning the relaxation field. They are more of a physical nature. The first condition is the so-called red field condition. It just means that the usual relaxation theory is valid only if the spinet's relaxation time is much longer than the relevant correlation time of the fluctuations we are looking at. And more important is a high field condition. With very viscous samples or with samples with restricted molecular fluctuations, there can be residual spin couplings which lead to local fields. And this means that spins are not relaxing in the external field, but in local fields. So one should make sure that the range we are looking at should be always larger than the local fields. So the total range that can be reached typically is from a few kilohertz up to 10 to the 8th hertz for protons, and this corresponds to fluctuation times from 10 to the minus 9 seconds up to 10 to the minus 4 seconds. Of course, at higher frequencies, this range can be extended by steady magnets or with shuttle devices where one shuttles the sample from the central field to the stray field of the magnet. Now, the statistical theory behind. As you may know, the spinet's relaxation rate is a linear combination of spectral densities according to the Bloch-Wagner's red field theory. And the spectral density has to be taken at angular frequency omega sub k. These are the allowed and non-energy conserving transitions of homo or heteronuclear spins. That is, single or double quantum transitions, or in the case of heterocoupled systems, also zero quantum transitions. Now, this spectral density is related to the correlation function via the Wiener-Khinchin theorem, which is actually a law. And this autocorrelation function represents the fluctuating spin couplings. So, the origin of these fluctuations, of course, is molecular motion. Let's consider dipolar couplings, for example. So we have maybe two magnetic dipoles, dipolar coupled, and the Hamiltonian of this coupling is shown here. It's a sum over all dipole pairs with a distance r sub aj, and this expression is describing the fluctuations of these coupled dipoles. If there is some intermolecular interactions, we have to take into account also these couplings to neighboring molecules. Now, this expression under the sum can be analyzed into two functions. There's a spin operator OD, which describes what transitions are considered. This means in homonuclear systems, single and double quantum transitions. In heteronuclear systems, there are also zero quantum transitions. This is of minor interest in the present context. What is important is this function f sub d. This function f describes the orientation and the distance of the dipoles, of the interacting dipoles. We have the distance r sub j, j, and we have the azimuthal angle and the polar angle. Now, when we form the correlation function of this dipolar interaction, we thus have to form the correlation function of these functions f. So it's given as the product of this function at time 0 times the function at the time tau at the conjugate complex version of this function, and we have to take the ensemble average. Spelled out, it looks like this. Important, we take the function at time 0 and at time tau and take the ensemble average. Now, the question is, how do we calculate these ensemble averages? Two remarks at first. I mean, it's quite important that we have to take the initial orientation of the molecule and the final orientation, irrespective of what happens in between. And then in principle, we have several correlation functions for the different multiple quantum coherences K. This is not very important. Normally, in most cases, we will get the same autocorrelation function irrespective of this order K. Okay, then let us further assume that the interactions are intramolecular, the distance is constant, so that only the spherical coordinates phi and theta fluctuate. These angles define the orientation of the dipole vector, of course, and the initial and final orientations are defined by the unit vectors u sub I and u sub f, as I've shown already. We will make use of two orientation probability densities. The first one is the a priori probability density that this characterizes the initial orientation, the probability for the initial orientation at time 0. And the second probability density is a conditional probability density. It gives the probability for the final orientation if the initial orientation was u sub I. So with these two probability densities, we can set up an expression for the correlation function. Here we have the solid angle element into which UF points, a final orientation vector. And this is the solid angle element into which the initial orientation vector points. So here we have the product of the a priori probability and the conditional probability. This product is just the probability densities that the initial orientation is u sub I and the final orientation is u sub f. And this has to be multiplied by the respective spherical harmonics of second order. So this is the function we have to calculate. Now, as an example, one can use any equation of motion, such as the diffusion equations or something like this. And let us consider the isotropic rotational diffusion of spherical molecules, for example. Then one finds that the correlation function is given by an exponential function, where tau c is the correlation time. And if this is the case, it's a straightforward calculation, but this is the result. So if this is the case, then we will have a Lorentzian spectral density, and this way we can predict how the spin lattice relaxation rate depends on the Lamarck frequency. Now here we have plotted this Lorentzian spectral density as a function of the frequency, and you see if we increase the correlation time of this fluctuation, of this rotational fluctuation, the spectral density will go up at low frequency, but will go down at high frequencies. So this depends on the correlation time relative to the Lambda frequency. If we look at a medium frequency, imagine you are measuring at a fixed frequency, you will see that we have a maximum of the spectral density. So spin lattice relaxation rate will have a maximum. At shorter and longer correlation times, the value will be less than at the position where we have this omega times tau equal to 1. So this is a very simple case, and processes which are of interest in field cycling NMR relaxometry are usually much more complicated. The best way to calculate a correlation function is just to remember that it's just the probabilities that there's no change after tau, no change of the orientation of distance or something like this. So if W of tau is the probability that a certain dynamic process occurs in tau, then 1 minus this W will be just the correlation function. What we need to calculate this probability is an equation of motion, which is specific for the model. We have already seen this example of the rotational diffusion. And secondly, we need information about any constraints of the dynamics. Example, imagine an entangled polymer liquid where we consider one tag chain, which is drawn here in red, and this chain is entangled by many other neighbor chains. And if this chain is to diffuse, it must perform a snake-like motion, which was called reptation by the Shen, who originally suggested this type of dynamics. Now, if we want to calculate the correlation function, we just have to take the equation of motion, which is a quasi-one-dimensional diffusion equation. I mean, a segment can only diffuse along one dimension, and have to assume that if there shall be no change, it's just the probability that the segment is still at the same position. And secondly, we need some topological information. This is given by the conformation of this chain. It's a random coil. It's, so to speak, the tube constraint. And the result, the straightforward result of this consideration is that in a certain time range, the correlation function is proportional to tau to the -1/4. And this means the spectral density is proportional to omega to the power -3/4. And thus we are expecting that the spin lattice relaxation rate will have a relaxation dispersion of omega to the -3/4. You can have a look at an experiment. In this case, we have studied polymers, polyethylene oxide, confined in a pore, in a tube, in a solid matrix. FEMA is a certain solid material. And here we have some data. Actually, this is a spin lattice relaxation time of deuterons. I mean, this is a deuterated polymer, so we can exclude that there will be any signal by the matrix. And actually, we have observed this power law, u to the power 0.75 in a certain range. Here we have some deviation. This is due to the low field limit which is most likely due to the high field condition, which is violated in this case. So this appears to confirm the prediction by Duchenne. However, if we look at bulk polymer the result is not so convincing. In this case, we get an exponent of 1/4, and this means we just have to modify the model if we want to apply, if we want to consider bulk melts. So this leads us to the typical protocol of field cycling studies. We start with a model of the dynamics. This can be rotational fluctuation, translational fluctuation, exchange, elastic modes, auto-directed fluctuation, and so on. And we make some predictions for the fluctuations of the couplings. So we get these functions F, we form the correlation function, spectral density, and thus we have some predictions for the spin lattice relaxation rate. And then we do our experiments and we compare the predictions with the results. And this gives us some feedback to the theory. If there's a good coincidence of the predictions with the results, it's fine. If not, we have to modify our model. Now, in many cases, we will have a superposition of stochastically independent dynamic components. And the question is, how can we form a total correlation function if we have these different correlation functions of these components? And of course, as a probability that there will be no change in tau, we have to form a product. It's a product, not a sum. And as an example, we can consider this case. We assume protons dipolar coupled to a paramagnetic ion. And here we have different components. For instance, as long as a proton is coupled to the ion, the whole complex can rotate. There will be rotational fluctuations. And then this proton, or the water molecule, will not be bound forever at this position. It can exchange, and it will modify the coupling in this way. And the third component is a spin relaxation of the paramagnetic ion, which also will modify the dipole interaction. So we have a product of three correlation functions for the three components. And as it turns out, all these functions are exponentials with three different correlation times. And if we spell out this product, we get the total correlation time, which is just the sum of the inverse correlation times. So that's the fastest component will dominate. It's a very simple example. But however, with real materials, and in the following I will talk about the pneumatic material HCB, the situation is a bit more complicated. A pneumatic material, in a pneumatic material, we will have some orientation of these elongated molecules. There will be a certain preferential orientation given by the director. This director can fluctuate as a consequence of the collective reorientations, and molecules can rotate about their long axis and can diffuse along this axis as well. So we have molecular reorientations due to rotational fluctuations about the long axis and due to collective reorientations called order director fluctuations, ODF. Now these components are restricted, unlike the example we have just seen. They are restricted. And this means the correlation function for rotational diffusion will not decay to zero. There will be a finite residual correlation at long times. And likewise, the correlation function for autodirector fluctuations will also have a finite residual correlation. When we now form the product, for the total correlation function, we just have to multiply all those terms. And what we find is the following. We get 4 terms. The first term, we get these lowercase functions characterized by the lowercase letters G, rotational diffusion, and G, autodirector fluctuations. If we restrict ourselves to a time scale much longer than rotational diffusion, then we can neglect this, because this correlation function for rotational diffusion will decay to 0 before these autodirector fluctuations become relevant. And at the end, we have a product of these constants, which is not very relevant. And what remains are these 2 products. So the effective correlation function can be approximated by these 2 terms plus an irrelevant product. So in this case, we have a sum indeed as an approximation. And this means that the spectral density will also be a sum, and consequently we have a total relaxation rate, which is a sum of the relaxation rate for rotational diffusion and a relaxation rate for autodirector fluctuation. But important, it's an approximation, and the condition is that the rotational diffusion is much faster than autodirector fluctuations. Now we can look at some experimental data. Here we have a comparison of the isotropic phase of this HCB. There's no dispersion. This means there's no finite slope. This means there is no correlation time or correlation rate of the fluctuations within this frequency range. This is in contrast to the pneumatic phase, where we have this peculiar nu⁻² dispersion, and here we have a violation of the high field limit. I mean, this special relaxation dispersion can be calculated in detail and predicted in detail, actually, for pneumatic fluctuations. And if you look, you can find the theory in many textbooks, and also in chapter 6 of my book, Principles of Matter Dynamics. Now let's turn to a further application where we confine the HCB, thematic material HCB, in a porous medium. Aerosil is a silicon material with a very large specific surface. And this means that molecules will be oriented at the surface, even in the isotropic phase, even if the bulk is in the isotropic phase, even above the isotopization temperature. So we have a surface-ordered phase in the pores of this material. For a test of what can be predicted on this basis, one can do a Multicolor simulation. One approximates the pores by a hollow sphere, and then we will have a ordered layer along the surface, and we have a bulk-like material in the isotropic phase in the middle. And then we consider the initial orientation of a molecule, for instance, specified by this vector, which can be desorbed, diffuse a while, and be reabsorbed at some other place. And so we will have different initial and final orientation given by this process, which we call reorientation mediated by translational displacements, RMTD. These are data measured in this system, and the lines refer to this Multicolor simulation. In the upper plot, we have assumed a constant width of this layer, 1 nanometer, and as a curve parameter parameter, we have varied the radius of this hollow sphere. And in the second plot, we have assumed a fixed radius, and we have varied the width of this surface layer. In both cases, we get a rough coincidence of these predictions. Now, if we compare this with bulk HCP, we just see again there is no dispersion at all. There are no fluctuations in this frequency range, while in this confined material we have this RMTD process and rotational diffusion of molecules. And this is an ordinary low frequency plateau which is reached if the frequencies are lower than this mean correlation time for this process. Now, this was a simulation, Monte Carlo simulation. How can we do an analytical theory? And this refers to porous media in general. We consider a material where we have some adsorbate fluid confined in a porous, a solid matrix. We have an adsorbate phase characterized by the index A, and we have a bulk-like fluid. And so we can distinguish different fractions of molecules with respect to their initial position and the final position. The fraction of molecules being initially in phase I, either A or B, and finally in phase J will be designated by F sub I J. And the correlation function of such a subensemble will be called J sub I J. And so the total correlation function can be formed as a sum for all four subensembles. Those molecules which are both initially and finally in the adsorbed phase, those which are initially adsorbed but finally in the bulk-like phase, those which are initially in the bulk-like phase but finally in the adsorbed phase, and those which are initially in the bulk-like phase and finally also in the bulk-like phase. Now, if we assume that the time scale, that the correlation time in the bulk-like phase is very short, so that the time scale of interest will be much longer than this correlation time, all these terms can be neglected. And the result will be, for this long time scale, just this first term. So the fraction of molecules that will be both initially and finally in the adsorbed phase, and the correlation function for molecules in this adsorbed layer. Okay, and because molecules are assumed to be in the adsorbed phase both initially and finally, we will have to consider an effective displacement along the pore surface. And this is enabled by the RMTD process, as we have already assumed. We have an initial position on the surface and a final orientation at the surface, and some curvilinear surface pathways. So this does not mean that the molecule is really diffusing just along the surface. It can also be desorbed and diffuse in the bulk and return to the surface. It's only important where the molecule is initially and finally, and what orientation applies to these times. Okay, so when we form the correlation function as usual, now we have the subscript 0 and S. 0 means initially, and S means in a curvilinear distance S along the surface. And we can analyze this expression by a surface correlation function. It's a probability that the orientation of the surface from here and here is the same. So it's just a topological function. And this is a probability that the molecule will diffuse a distance s, a curvilinear distance s from here to here. This is a correlation function. Now, the topological surface correlation function can be described in this way, just the spherical harmonics of second order at the position 0 and at the position s. And the propagator along the surface is just a quasi-two-dimensional probability density for curvilinear displacements s in the interval t, or tau. This should be tau. It's favorable to transform the real space, S space so to speak, to a Q space, a wave number space, via a Hankel transform. And then we get some new functions, S and P with this tilde above. Now this function S of Q, it's called the orientational structure vector, it's just the surface correlation functions, and here we have the zeroth order Bessel function times a certain distance element along the surface. And the function P of Q and T, the surface propagator, so to speak, is given by the real space propagator along the surface times the zero order Bessel function again. It's just a formal transformation, which is not so important in this respect. But the advantage of doing this, that we get a very general propagator, the so-called Levy propagator, which is given by a power of the wave number Q, which describes the surface roughness. And this exponent alpha can be in a range from 0 to 2. If it's 2, then we have ordinary Brownian two-dimensional diffusion along the surface. If it's less than 2, then we have anomalous diffusion. And the special case is if this exponent is 1, then we have Levox. What is a Levox? I mean, this is again a surface, and you see in white this pathway, this trajectory of a particle, of an adsorbate molecule. This can be desorbed, make some excursion to the bulk and returns, and diffuse again along the surface, make again an excursion, and so on. And what we have, in fact, is if you just look at the surface displacement, we have jumps from here to here, we have a jump from here to here, and jump from here. And this code of trajectory are called Levox. And as a process is, I mean, here we have this term bulk-mediated surface diffusion. It implies that there will be desorption, bulk excursion, and reabsorption. Now, if we use this notion for our RMTD process, we can assume rough surface and initial orientation, final orientation, and there can be some excursion to the bulk. If you assume that this obeys the Levy statistics, then we will have a Cauchy propagator along the surface. You see, it's here we have the distance s, the curvilinear distance s. Here we have time, and there's a constant c. Now, in an experiment, we can compare this with a similar situation, but now in a case where this adsorbate fluid is frozen. In many porous media, there will, when you freeze the adsorbate, then there will be a liquid layer along the surface. It's only 1 or 2 molecules thick. And so we have two situations. Above this freezing temperature, we are expecting this Levox statistics or Cauchy propagator. Below this freezing temperatures, molecules will be confined in this thin layer, and there can be no excursion to the bulk. So we are expecting a Gaussian propagator, the ordinary two-dimensional Brownian motion. And this can be tested in an experiment. In this case, we have studied DMSO in B10. It's silica, porosilica glass with 10 nanometer pore size. And you see if the adsorbate is unfrozen, we get cis power law. If it's frozen, we get cis power law. And here we have again the influence of local fields. Now, in order to describe this for the two situations, we need to make some assumption of the surface topology. And the quite general, relatively simple assumption is to assume a power law. I mean, this orientational structure factor in the Q space can be assumed to obey this power law with an exponent chi, which can vary in this range because of obvious reasons. And then we would expect if we calculate the correlation function with the formulas that I've just shown, we get this power law for the correlation function, and this predicts the split lattice relaxation rate proportional to omega to the minus chi. And this can be compared with the non-freezing surface layers where we expect a Gaussian propagator. With the same assumption, we get a power law omega to the minus 1 plus chi divided by 2. So we have two different predictions, and we can fit these laws to these experimental data, and we find a common exponent chi, 0.5. In both cases, also we have the same topology, the same material, but we have different dynamics, Cauchy or Gauss. So this shows that both situations can be described by this assumption for the surface topology. Now let me describe some last example, which is related to this RMTD process, the flow relaxation process. One can superimpose hydrodynamic flow with ordinary Brownian motion. So we press some fluid through a porous medium. And what we are expecting is that if this fluid flows along a rough surface, the displacement of molecules, of adsorbate molecules from here to here will be enhanced. There will be some additional displacement by the hydrodynamic flow. And this can be described by an equation of motion, so-called convective diffusion equation, which gives us the surface propagator for displacements S, curvilinear displacements S along the surface. And you see there's an additional term, the flow term. It's the velocity, and this is the gradient of this surface propagator. Now, the spectral density can be formed in this way. If we solve this solution, if we form the correlation function, we end up with this double integral. First, we have a distribution of orientational structure factors, different values Q. So we have to integrate over all wave numbers describing the rough surface. And then we have very likely distribution of the velocities, of the flow velocities. We have to integrate from a minimum to a maximum velocity. And as an assumption, we can assume that these distributions are partition, so for the wave numbers and velocities. And if we do this, we end up with this expression. Spin lattice relaxation rate, a certain range from maximum wave number to a minimum wave number, a certain range for the velocity, 0 to the maximum velocity. And as we see, the spin lattice relaxation rate depends on the velocity. One can do a multicolor simulation in a model system and look at this window. This range here shows where we can expect an effect. It's only at very low frequency. There should be some effect, and so we can look at low frequencies and at high velocities. This Pickley number specifies displacements by flow relative to those by diffusion. And the experiment one can do is one can use accommodate. It's a material used in chromatography columns. It has a bimodal pore size distribution, the nanometer, micrometer range. And the result is shown here. Spin lattice relaxation time versus frequency. Here we have in black the data for the static case, no flow. And the red data points refer to flow, 2.4 milliliters per minute through that particular sample. Now, we can describe this. I mean, the solid lines are vertical lines for a maximum velocity of 0.04 meters per second, a diffusion coefficient in water, that's the usual water diffusion coefficient, and wave numbers, limits of the wave numbers, the lower of the large pores, we expect this given from this value, and for the small pores given by this value is this value. So it's a reasonable range predicted by this material, and we have this effect. The effect is small, it's definitely small, but it's finite, and this shows that we can influence this process, this flow process on spin lattice relaxation. Okay, let me finish by listing some take-home rules. First, we have seen that the correlation function is calculated as the probability that there will be no change of the orientation and of the distance in an interval tau. The basis of this probability is an equation of motion, often in combination with topological constraints, if existence. I mean, we have two sources of information of the process. Equation of motion can be a diffusion equation, can be this convective diffusion equation, can be an equation of motion for elastically coupled molecules, and so on. The Bloch-Wagner-Schwertfeld theory is valid only for relaxation of spin lattice relaxation times larger than the collation time. It's just the Redfield condition. Constrained reorientation, as we have seen here in several cases, lead to local fields, residual spin couplings, and these fields limit the ordinary relaxation dispersion at low frequencies. Can be relevant in the usual frequency range. The total correlation function of superimposed components, as they often occur in complex material, are calculated as a product of the corresponding partial correlation function, and only in favorable cases we can make some approximations leading finally to a sum of relaxation rates. So in this tutorial we have seen rather complex dynamics, liquid crystals, polymers, and porous media. And if you are interested in more examples and so on, you can refer to the books I have listed here: the Field Cycling NMR Relaxometry book and my book on Principles of Soft Matter Dynamics, which have appeared in recent years. So finally, I would like to mention my co-workers, with whom I enjoyed cooperation over many years. All these names that can be found in the books and citations and so on. And finally, I would like to thank you for listening, and best regards from all on the Danube. Thank you.